So thank you very much, Yula. Again, I said it like the first time, I feel not only very glad, but as well honored to have the possibility to interact with this GAUSS, the Gothenburg Astronomical Jazz Society. Very good. Galaxies. Actually, I told you last time that this is a little bit, it's not a repetition, and try to understand more about the dynamics of this galaxy from a popular level, since you are invited mostly for having a little bit of dynamical ideas. Very good. So I will not repeat what a galaxy is, because this, you have learned it. First of all, you know it very well, and then if not, you have learned it from my previous talk. So if you have doubts, then feel free to ask at the end. But here now we are concentrating on how galaxies live from a dynamical point of view. And the first thing that I would like to convince you is that they are stealing from the poor and giving to the rich. So it's totally the opposite of Robin Hood, okay? It's very, very unethical if we think about our moral principles. And why they are doing that? So let me explain something about the galaxies, okay, their shape with these dynamics. So as I anticipated last time, galaxies like our own Milky Way have a spiral structure. Okay, here you see a very, very, very nice example is the Whirlpool galaxy, which has two very, very symmetric spiral arms. And the next example is another very, very nice example of spiral galaxy, which contains is that these are really material arms, like a mine. Okay? But this is actually, as we explained last time, it's not really possible because it's faster in the center than outwards. This is, I'm talking not the velocity, but talking about the angular speed. Okay, so if these were material arms, and then galaxies, when they rotate, they would be very, very, very tightly wound. And it is very simple to make a rough calculation. The age of the universe is about 10 billion years. The time that it takes for a galaxy to rotate is about 100 million years, okay, within a factor of 2. And then it means that each galaxy, like a Milky Way, is able to rotate about 100 times. Okay, and so we should not be able to see any type of beautiful spiral arms like this. Okay, so this is actually a very, very important dilemma which has challenged the mind of people for very many decades. It's called the winding dilemma. And the other dilemma is, of course, that these spiral arms are very, very huge. From one side to the other, you go like something like 100,000 light years. So they're not just little vortices like the one that you see in fluids, okay? And so how is it possible that they are there? So we said if they're not material arms, what type of explanation can we have? So people argue, first of all, in terms of intuition, and the first intuition is to have waves. No? It's like when you have a lake, you throw a stone, and you will have a lot of circular waves produced. So the question now is, okay, circular waves, but here we are spirals. Well, but if you have systems which have a velocity more in the center than outwards, then you have a property which is called shear. Okay, so the layers is not like a solid body. And this will make the waves not circular, but spirals. I suggested last time that you can even make an experiment in one of these rotating swimming pools and throw yourself away there. But then still the problem is not solved because whatever type of wave you are producing on the Earth, then this wave is damped after a certain way. Okay, so these little waves that you produce in a lake, then they become small amplitude and they disappear. Whereas when we look at galaxies, the arms are always there. So how is it possible that we don't damp these waves? And now here comes, this is a problem so complicated that it actually took a half a century to be solved. Okay, and so and since it is so complicated, I will not go into details. I just sketch a very, very, very simple dynamical analogy. Okay, so that you can understand how this is possible. So then In this little simple dynamical analogy, you have these spiral galaxies, of course, which are either normal, just with arms, or barred, with a bar and the arms. So the mechanism, if you want to do an analogy, is a little bit like when you have a ball, a cannonball on the top of a hill. Okay, but the hill now it's quite undulated. So if you leave the cannonball alone to itself, then the ball will go away, because here you have a gravitational field, will go away from its initial equilibrium state, which was unstable, and then at the same time oscillate. Okay? So let me just explain a little bit why this is called overstability in physics. No, Julia wanted to have a little bit of dynamical concepts. This is a little bit funny. This name, in astronomy, in astrophysics, you always find very strange names. And this name was created by a Nobel Prize. It's actually Chandrasekhar. Is an Indian with a head like, not the head like this room, but probably like the whole Gothenburg or even more. He got a Nobel Prize, and this person was a pioneer in stellar dynamics, in plasma physics, hydrodynamical instabilities, stellar structure and evolution, and everything you want. It was really a genius. And what was happening, I know, because my supervisor, Dennis Sharma, was sharing a room with him in Oxford. And this Chandrasekhar, this Indian who discovered this mechanism, was always going to the office with not an A4 paper, A0. It's A0 is like a poster. And it was starting in the morning from the top left, go on writing equations up to the, without making mistakes, to the bottom right. And so he was writing books. So he was as well full of humor. And this is the reason why this is called overstability. It does not mean more stable than otherwise, but it simply means that they are unstable, but with oscillations implied. So the difference between them, between normal and bar galaxies, according to this analogy, is that the bar galaxies are more overstable. So it's like that the hill is steeper. Okay, it still has the same oscillations, but it's steeper. So the system is more stable, and then you produce naturally a bar. But then you can ask yourself, what are the implications? How is it possible that you can create these overstable systems? I mean, somewhat you have to give the energy. How is it possible that you generate this? Well, then you come to the next slide, which is a little bit humorous as well. Was Robin Hood wrong? Okay, so in order for a spiral wave, for this wave to be able to survive, to become overstable, they need to transport angular momentum and energy outwards. This angular momentum energy are very, very important quantities that I think all of you have studied in the gymnasium. So, but let us see, how can we understand this? Well, let us first look at this first plot. Okay, this is what is called a rotation curve of a galaxy. So when we have galaxies like our Milky Way, they are rotating. Okay, and the velocity is not fixed, but is differential. So it's rotating. The patterns, the angular speed is higher in the center than outside. So by looking at the hydrogen emission line, the 21 centimeter that one can actually detect with telescopes like in Onsala, then you can actually, by means of Doppler shift, you can really know how the velocity, how these systems are rotating versus the distance from the center. And generally, rotation curves of galaxies have these very nice features that they, first of all, increases linearly with the distance, and then beyond a certain turn around radius, they become very, very constant. This seems very strange because this constant is even when you go very, very, very far away from the galaxy, even 3 times, 4 times more far away than the optical image. And this is not intuitive, because if I take a point like the sun, okay, some very concentrated mass, and I go very, very far away or even close, then I know that I can predict the circular speed by a balance between the centrifugal force, which tends to push the planet outwards, and the gravitational attraction, which tends to take the planet inward. And this is very simple. The gravitational force, okay, acceleration is a gravitational constant times the mass over the square of the distance. And the centrifugal force is simply the square of the speed over the distance. So what would you expect going very, very far away from a galaxy? You would expect that the rotation curve declines like 1 over the square root of the distance. Okay, whereas no galaxy does this. So why does not? This is actually was one of the first evidence for the presence of dark matter, okay, as we discussed last time. But this is another story. So now that we know the velocity of a galaxy as a function of the distance r, then we can easily calculate the angular momentum and the energy. And since now we don't have just one body, but we have a collection of stars, what one generally does is considering the specific angular momentum. So the angular momentum divided by mass, and the energy divided by mass. This is what it means specific. And so the angular momentum is simply the velocity times r. Okay? So since here the velocity was rising linearly with a radius, now here the specific angular momentum rises like quadratic. Okay? Simply because it's this times r. And where instead the velocity is constant, then the angular momentum increases linearly. Okay, very good. So you have different behaviors. And very similar consideration can you do as well for the energy, for the specific energy. Okay, so the specific energy is proportional to 1/2 the square of the velocity. Okay, how is it possible? Look, you know this. Why I write here just the kinetic energy? This is actually the total energy, but why here I don't write the potential energy? Luke knows this. And look.
I wouldn't say I.
You remember when you came to the astrophysical dynamics the first time? We were talking about a very, very important theorem, which is called the virial theorem, no? So all matter which has time to set into equilibrium, you have a balance between the kinetic energy and the potential energy, okay? So that the total energy becomes minus 1/2 v squared. Okay, so this is actually is very simple to illustrate with circular orbits. Okay, but this is true actually for whatever system. So what happens now then to the specific? Thanks, Luke. What happens now to the specific energy? Okay, it's proportional to the square of the velocity. So where the velocity was increasing linearly, then the specific energy increases like quadratically, like r squared. And where the velocity was constant, then as well the energy is constant. Okay, so but what happens now? So what allows spiral waves to grow in time and to resist the dissipation, which is very, very natural agent, is that they transport angular momentum and energy from the inside of a galaxy, from the inner regions of galaxy to the outer regions. Okay, but if you look in these plots, the inner regions of galaxies are poor in terms of angular momentum and energy, whereas the outer regions of galaxies are rich because they have bigger angular momentum and bigger energy. So what spiral waves are doing for surviving is to create even more imbalance, okay? Steal from the poor and give it to the rich. So this is actually the very first unethical behavior of galaxies, which we have been explaining today. But you can ask this, since I know that Julia wants to have a little bit of dynamics, because she expressly asked me the first time, and then I show you as well another plot where I want to tell you a little bit more about this amplification mechanism. So the title is as well here a little bit humorous. Not laser, but waser. And in fact, the mechanism which gives rise to this wave amplification by stimulated emission of radiation, okay, is exactly the analog of laser. Okay, laser act on atomic, very, very little atomic scales. Here we have galaxies which have a very similar mechanism of amplification of their waves. And how it works? Well, whenever you have a wave phenomena, oscillatory phenomena, then you have very important places in your space which are called resonances, okay? And what is a resonance? You remember that in your gymnasium courses, you've studied the harmonic oscillator, okay? So you have a spring which is fixed in one part, and then you do like this, and this is moving, okay? But what happens now? So if I do like this, choop, 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 I have a pendulum, and I leave it from like this, the pendulum will do like this. So this is equilibrium motion. But now what happens if I perturb this motion with a force whose frequency is a multiple of the natural frequency of oscillation? So suppose this is the natural frequency of my spring, and then I take a force which has, for example, twice larger frequency or 4 times more. It means that where the two things will be in phase, and the motion will become more and more ample. Okay, and the same thing happens actually, is very drastic, for example, when you construct bridges. Okay, so why bridges are very complicated to construct, and you don't do this only with one material? Because imagine to have a lot of soldiers walking, okay, and if this march is exactly a multiple of the frequency of the natural oscillation of the bridge, then the bridge could break. Okay, so the concept of resonance is very, very, very inbuilt in us. Okay, as well, think about a pendulum and think of doing like this with a frequency which is proportional. The pendulum goes more and more like this. Okay, there are 3 of these important resonances in galaxies. So here you see a very schematic plot where in the horizontal part, you see the distance from the center. And you first of all have a resonance which is called co-rotation resonance, where the spiral waves have the same circular speed as the galaxy. Okay, so this is a frequency which are very similar. This co-rotation resonance, you will see in a while, has the property of amplifying the waves. Okay, like when you have a forced harmonic oscillator. But there are another type of resonance, which is called Lindblad resonance. And this Lindblad resonance is actually like sucks the energy of the waves. So it acts for damping the waves. And generally you have not one, but generally 2 Lindblad resonances. One at large distances, which is called the outer Lindblad resonance, and one at short distances, which is called generally the inner Lindblad resonance. Lindblad was a Swedish people, so Forza Swedish, with Sweden. So what happens? And then you have, of course, a bulge, the spheroidal component of the galaxy, which we have been describing last time. And if you have galaxies like our own galaxy, then the bulge is at the bulge is after the Lindblad resonance. But if you have galaxies which are very, very, very irregular, like, for example, Magellanic Clouds, which are satellites of our galaxy, then the bulge turns out to be before the inner limb resonance. And the mechanism now then is the following. So suppose that how is it possible that you can propagate waves and they can be supported? Well, imagine again that you perturb your system, which can happen by means of a satellite galaxy, which is accreted. Okay, then you will generate spiral waves, which suppose that they propagate from the bulge outside. Now, when these spiral waves meet the corrotation resonance, something amazing happens. It's something which is called the quantum tunneling, okay, that you will study if you are doing physics. You will study this in the third or fourth year when you will hear how laser works. So the wave is partly refracted away, so towards larger distances, and partly reflected back. The wave, which is refracted, has a similar amplitude as the coming wave, and this will reach the outer limb resonance and will be absorbed. Okay, so TAFCO A. But what happens now? The wave which is reflected back, this has an amplitude which is larger and twice larger than the incoming wave. So how is it possible? How do we understand this in terms of conservation of energy? How is it possible if I have an incoming wave, then I have this disappears, becomes another wave of the same amplitude, and then here a reflected wave with twice more amplitude? Huh? Does any one of you think about this? Huh? Mysteries. This happens as well in the quantum in atoms. Well, because the energy change sign is negative, okay, so there is more potential energy in the wave before the corrotation than after, okay? So what happens? That energy here is positive, here is negative. So when you have, in the beginning, the amplitude was -1, here you have -2 plus 1 is -1. So you don't violate the conservation of energy. It's just that this dynamic is more complicated than what we are used on the Earth, but quite similar to what happens in lasers. So this is why it's called waves. Okay. So then these spiral waves, which is reflected, then moves towards the bulge, and the bulge then has the property of reflecting like a mirror the wave. So the wave comes back like here, okay, then meets again the corrotation resonance. A part gets refracted and then absorbed, but the other part gets amplified. Okay, so this is the way, the very complicated way that it took 50 years for people, of course. Now here I'm representing just the sketch, but imagine that the people who find these, okay, the very, very complicated equations, then they thank God for illumination. Okay, this is a little bit like what I was telling about the way, why spiral waves succeed to, first of all, what type of instabilities they are, why they are against our moral sense, and the actual mechanism, which is very similar to the laser.
Okay. We have a question in
Sure,
the chat,
sure, please.
where someone asked, we were talking about the spiral waves, but
yes, good, bravissimo, bravi, ask. Who is going to ask?
It was Eric, I think.
Henrik?
Eric, I think you can unmute yourself.
Eric. Yeah, Eric, unmute yourself.
He says that his mic isn't working.
Okay. Should I go on or wait? We go on because you will see that there is a lot of of things which are coupled. Okay, so Eric, so then you can ask a little bit later. Very good. Okay, social parasites or heroes. Okay, so now that we think to have understood the spirals and bars in galaxies, and it's actually a very well established observational fact that many galaxies, they have smaller bars and smaller spirals within the main. Okay, so if you have here a primary bar, you can very often find so primary bar generally has a size of about 10,000 light years. Okay, within these, you generally find mini bars which have a size of about 1,000 light years, so about 10 times smaller. Okay, so, but this is really terrible. Julia, how is it possible that we can have this? Because the size of these mini bars is such that they are inside the inner limbal resonance of the primary bar. So if what we have said before is true, okay, every type of phenomena which is wave and it's before the inner limbal resonance gets sucked, okay? But this is not here, but this is not what you observe. So this is another very strange way. How is it possible that this secondary bar, these bars within bars can exist? Well, again, this is a little bit difficult and took very many decades as well for people to understand. This is a manifestation of what is called mode coupling. So imagine to have, again, not just one pendulum, but two pendula, one after the other, okay? Like this. Or two springs, the first one and then another one. So they are free to move like this. So what happens is that our Mother Nature is so smart. So in order to be able to survive these secondary bars, okay, this is a little bit like Darwin, okay, the survival of the strong species. They are in such a way that the co-rotation resonance of the secondary bar, so the one that allows the bar to be amplified, coincides with the inner limbal resonance of the primary bar, so where the material is sucked and the energy is sucked from the wave. So this is the reason why they can be considered, the secondary bar, as parasites, okay? Simply because they live at the expenses of the primary bar or the primary spiral. So you see mode coupling. You see, this you will study in physics 1 with the oscillators, and this is an astrophysical example of mode coupling and selection. Okay, if they were not like this, that the co-rotation resonance of the little bar, if does not coincide with the inner limbal resonance of the primary bar, then you will not have these systems to exist. Okay, oh, but why did I say heroes? Ha ha ha, wait a second. Here there is another object here. What's that? Can any one of you just shout what you think is that inside in the center? We have mentioned this already last time, so you should know this.
Would that be the black hole?
Bravissimo, Eric. So these are actually a supermassive black hole. And as I told you last time, to all of you, supermassive black holes were hypothesized just for explaining the enormous power emitted by quasars, by quasi-stellar radio objects, which were emitting as much energy as an entire galaxy, okay, from a very small region, or from galaxies like Seyfert and others. Blazers and others. But as I told you last time, we have very strong evidence provided by the Hubble Space Telescope, which is orbiting around the Earth outside the atmosphere, so it's a very, very good sensitivity and resolution, we have strong evidence that all galaxies in the universe, at least the ones that we can observe, including our own Milky Way, possess a supermassive black hole. And this supermassive black hole, supermassive, what it means? It means that it's not 10 times bigger than the sun. It means from 1 million to 1 billion or even more the mass of the sun. Okay, and this you have it in our galaxy. The Milky Way has a supermassive black hole of about 2 million solar masses. Well, Alessandro, you are telling now that there is this supermassive black hole, but how can you form it? These black holes must eat. So people thought that now we can produce these supermassive black holes in the very early universe by having stars which are very, very big. Why is it possible? You see, in the local universe, so in the universe that we can observe close to our Milky Way, you never find stars which have a mass larger than about 200 or 300 solar masses. Why not? Because, and here I come, Shady, you were asking about the radiation pressure. You sit here. When you have a star, an object which has mass 200 times more than the sun, and the gravitational field is so intense, it has submitted this gravitational catastrophe, which I explained last time. So it's very, very hot. You are burning hydrogen into helium. Well, the energy of these photons, which are emitted, they bump onto the matter itself, and they exert a pressure, exactly like the normal particles. So there is a critical mass for stars in the present universe, which is about 200 solar masses. Okay, if it is more than 200, then this radiation pressure is larger than the gravitational attraction, and the stellar disappears. But in the early universe, so I was talking about just 1 billion years after the Big Bang, you can actually produce stars as big as 1,000 or actually 100 or 10,000 the solar mass. And this is possible because in the present universe, there are elements, mainly hydrogen, helium, and a little bit, about 2% of what astrophysicists call metals. In astrophysics, metals are elements which have atomic weight more than helium. And this radiation pressure is very sensitive to the amount of metals. In the early universe, these metals are produced by supernova explosion, because the more a star is big, the more it will first burn hydrogen, then it will burn helium, and then carbon, and so on. So in the present universe, there is a critical mass because you have this about 2% of metallicity. But in the early universe, when there were not yet stars, okay, they were not the normal stars, then stars could become as well bigger, precisely because there was very, very little metallicity, and the energy of the photons emitted by the stars could not couple strongly with matter. But still, this is not the end of the story, because at most you can produce in the universe black holes of a mass no more than 1,000 times a star. Here we are talking about a mass of millions to billions times. How the hell is possible? You must then feed the black hole. So the galaxy has to provide gas, and this gas has to feed the black hole. Okay, but how can you do this? But the obvious argument is that gas is viscous. So when you have something which is viscous, it loses energy. So if the gas is initially in circular orbits, because of this loss of energy, it will try to spiral towards the center. and then ultimately possibly reaching the black hole. But this cannot be either, because one can make a very good calculation with the viscosity of the interstellar gas and finds out that it's so little that it will take for the gas about much longer than the age of the universe for being accreted by a black hole or by the supermassive black holes. So somewhat you have to have some extra agent. And how can you convince gas to spiral? Well, by losing angular momentum, one would say, from a point of view of a gymnasium student. From point of view now of people who are listening now here, is by transporting angular momentum and energy outwards. And this is possible with spiral waves and with bars, okay, simply because they are non-axisymmetric, they exert torques. Oh, so what happens that the primary bar and the primary spiral are able to transport gas until the inner limb resonance. Okay, so it's about 1,000 light years from the center. But without anything else, the gas would stall there, would remain there. So what the secondary bar are doing is, since they are coupled and synchronized with the primary bar, they are able, when the gas reaches the inner limb resonance, enters as well the corrotation resonance of the little bar, and then moves further inside the galaxy, and can reach distances of just a few tenths of light years, where the gravity of the supermassive black hole is bigger than the gravity of the galaxy. Okay, so you see here now why I was saying that this secondary bar or secondary spirals are parasites. Yes, because they suck energy from the big bar and the big spiral, but as well heroes, because they are somewhat enabling a gas to feed the supermassive black hole. But the story is not like this. They're killing their parents. Julia, again, nobody under 18 years old today? Can I go on without problems? Okay.
I think so.
I think so. Okay. So if there is someone below 17 years old, please eventually do like this and like this, okay? Because this is terrible. Okay. What happens then to these supermassive black holes? Well, when these supermassive black holes are fed by this bar bigger and bigger. So you can imagine parents who are spoon feeding their son like this. The black hole does not do anything else than eating. And they are the primary bar and the secondary bar who are doing this spoon feeding. But what happens is that when the supermassive black hole becomes larger than about a few percent of the mass of the galaxy, then the gravitational attraction of the supermassive black holes becomes so strong that it perturbs the orbits that make up the bars, not only the little bars, but as well the big bars. So what happens? That this gets totally destroyed. Okay? So you see, this is a very, very, very unfair fate, destiny of these astrophysical objects. And so you understand why this field is so fantastic, okay? Because you have multi-scale relations in spiral galaxies. Spars and bars on large scales, spars and bars on smaller scales, and central supermassive black holes. Great. So then, this is not the end of the story. We have seen last time as well that galaxies are as well fighting violently with their neighbors. And last time I told you that whenever two galaxies merge, whenever two galaxies gets closer to each other, well, something drastic happens. And this something drastic happens is that the gas from one of the galaxies gets somewhat transported away and gets compressed by tidal fields, like the moon and the Earth. Well, you have it as well when you have any other objects. The difference in gravity between one part and the other produce tides, which are very, very strongly compressing the gas. A gas then becomes unstable and produces new stars, which you see here. But then now comes the paradox, okay? And then I want some of you that explain this paradox. As we explained last time, this happens only in the gas and does not happen for the stars. So even though these galaxies seems very perturbed, in reality, the distance between the stars is enormous. Just to make an example, imagine the sun, 1 million kilometers in diameter. The closest star is about a few light years. 1 light year is 10,000 billion kilometers. So we have many orders of magnitude. So stars in a galaxy, they are so rarefied, okay? But even gas is very rarefied because the typical distance between molecules of the interstellar gas is like the distance between the Earth and Jupiter, is about a billion kilometers, 10 to 9 kilometers. So then my question to all of you, how is it possible that when you have two galaxies which are merging, gas is able to get perturbed very much and then produce new stars, but stars are almost nothing happens to them? What is the difference between gas and stars from this dynamical point of view?
Like you were alluded to, the stars are already far away from each other. So gas will collide electromagnetically, whilst the stars will only collide gravitationally. So
Bravo, bravissimo, Eric. And what does this imply? When you have molecules which collide, what happens then? Gas is radiating, okay? And is viscous and radiating away. So gas can lose energy and angular momentum, but stars cannot. You get, so this is the fundamental difference, dynamical difference between stars and gas. And this is why gas, because of this dissipative nature of interstellar gas, can lose the part of the orbital energy, so can go very, very fast towards the other galaxy, and then, of course, gets compressed. Okay, so you see here that stars and gas, even though both of them are very rarefied and both of them belong to the same system, behave totally different, because gas dissipates, can lose energy, and so lose orbital energy. Stars can't. Great. Then last time we have seen, we are towards the end of the story, okay? Last time we've seen that you can even cannibalize, galaxies can even cannibalize whoever comes close to them. Clusters means that you don't have one galaxy, two galaxy, or 100. You have thousands to millions of galaxies together, okay? So I show you again in the video and look very close to what happens close to the center and explain me why this happens. Okay, so look very, very close to the center, what is happening. Okay, and so we've seen that these galaxies that form in the centers of cluster and supercluster of galaxies they are beasts. They can be up to 10 to 13 solar masses, which means 100 times bigger than normal. It's the difference between an elephant and a person, a human being. So last time we already said that we cannot understand this in terms of gas dissipation, because between these galaxies there is a very, very, very little gas hot, which is absolutely almost nothing. So then my questions to all of you, how is it possible that these galaxies can anyway lose orbital energy and sink towards the center? Who has some idea about this? The mechanism, I remind you what we said last time, is called dynamical friction. The person who found out this was again this Chalmers, this Indian Nobel Prize with a head like this, who was doing everything in astrophysics. Okay, and in the 1940s, he found out this mechanism. But there is a very simple way to understand it. So I would like some of you to shout, Alessandro! It is possible because choop, choop, choop. So, some can shout. Luke, would you like to shout?
I wouldn't shout perhaps, but like, isn't this the same thing as doing gravity assists in KSP? And like, so I searched the internet for this after last time. But like, you have gravity, and if you move, like, objects that are close tend to, the relative velocities are reduced.
Yeah. Yes, but why? If we want, very good. This is called polarization. Okay, polarization waves. But very good look. But let us explain this in a simpler way. Okay, so this is made possible by a fantastic combination of the way in which a gravitational force scales with the distance. Okay, so the gravitational force scales like the inverse of the square of the distance. Okay, so if I take two objects and I put twice apart, the gravity will be 4 times less. Okay, but so you could imagine that the galaxies which are very far away, like these and these, do not do anything to each other. But life is not as simple. In reality, the gravitational attraction only depends on the distance. So when I have a distance r, my gravitational force decreases like 1 over r squared. But how many objects I have at the same distance? If the objects are distributed more or less homogeneously, the surface of a sphere increases as well, like the square of the distance, the square of the radius. No? So what happens is that the net effect of gravity is the same whether you consider very, very close objects or very, very far objects, simply because there are many more far objects than small objects. Okay, look. So what happens is that each galaxy, when it's moving, it's like tightened with a lot of ropes to all the other galaxies. So it's doing effort, it's doing work, and this work subtracts part of the orbital energy. Okay, so this is a fantastic. This dynamical friction is actually arises because a fantastic combination between the scaling law of gravity. So if gravity would not scale like 1 over r squared, but would be like 1 over r cube, you will not have this phenomenon. So you see how fine-tuned our universe is sometimes. Great, thank you very much. So now we are at the end of the talk, and I summarize the abstract the summary that I gave to Julia when I suggested this talk: stealing from the poor and giving to the rich, killing their parents, fighting violently with their neighbors, or even cannibalizing whoever comes close to them. Is this a portrait of our society? No, awfully. This is how galaxies live. Right. So I am very, very glad now if we have questions and so on.
Yes, I have a question about the supermassive black holes.
Yes.
Basically, how do they find themselves in the middle of the galaxy? How do the galaxy?
Bravissimo, Henrik, bravissimo. Well, okay. Now I tell you, instead of giving you the answer, I ask some of the other students to give the answer. It's a mechanism which we have precisely been talking about in the last 5 minutes of the talk. So it's about the
dynamics.
Brava, dynamic or friction. When you have supermassive black holes, okay, because this is Henry's question is very nice, very good. So in reality, what happens that obviously when you have a black hole, okay, it will always be in the center because the material that gets transported can always be transported by the waves, and the gas is spiraling towards smaller distance. But suppose now that you have galaxies which are merging. So in principle, you have as well binary supermassive black holes. And in principle, one supermassive black hole could be in the center and the other one could be very, very far away, still because the other galaxy is approaching. But the supermassive black holes are as well dragging with their own gravitational field the other stars and the gas, okay? And so they are losing their orbital energy for the same phenomenon, dynamical friction. So if you wait enough time means something like 10 to 9 solar years, okay? 10 to 9 means more or less a few rotation periods of a galaxy, even though there has been a merging with another supermassive black hole, these other supermassive black holes would have time to spiral, lose energy, and go towards the other, very, very close to the center, because of dynamical friction. Okay? Thank you for this very interesting. So you see then that you have some key phenomena like wave amplification, dynamical friction, which are very, very recurrent all the time.
I see Samantha has a question. She was wondering if you could repeat that with the harmonic oscillator, because she didn't quite understand it. She
very
is
good,
a gymnasium student still.
Very good. Would you tell Eric or someone with the chat, because I cannot see, what exactly would you like to ask about harmonic oscillator? You are talking about the bars within bars? Are you talking about this? You would like to understand more these?
She hasn't. Okay, let's see. Yeah. She might not understand what the word is. She's talking. She was confused about the springs.
Springs. Very good. Henrik, how do you say spring in Swedish? Fjäder. Fjäder.
No.
Fjäder.
Yeah, I'm not Swedish myself, so I'm always confused.
Very good. Luke, it is fjäder. Fjäder, very good.
Yeah, it is.
So, very good. So, Samantha, you imagine that you have a wall. Attached to this wall, you have a spring. This spring, is fjäder, okay, with a little ball. And then suppose that attached to this little ball, you have another spring with another little ball, okay? So you don't have just one harmonic oscillator, but you have two harmonic oscillators, the first spring and the other spring, which are related. They are not decoupled, they are coupled, okay? So because of this coupling, you cannot just move them as you like. Their frequency of oscillations, they will be multiple of each other, okay? And the same thing happens when you have bars within bars. Okay, so the big bar here, and here you have the little bar. The little bar exists within the big bar and should in principle not exist, because inside the big bar you have the linear resonance, which is absorbing all waves and all bars and all spirals. So the only way for this little bar to survive is to suck the energy that the big bar is sucking from the rest of the wave. Okay? And this can only be done when the co-rotation resonance of the little bar, so where the bar rotates at the same speed of the disk of stars, is exactly at the same place as the linear resonance of the big bar. Okay, so in principle, you can see these little bars like a parasite. Like, for example, how do you call it? Is it's in English now. You know, when you go in the forest, there are things which go there, and it's like you fästingar. How do you say this is in English? But you understand, okay? So somewhat, these little bars are like this festing. You know, they are parasites who are sucking their energy from the primary bar. But they are as well heroes because they are giving this food to the supermassive black holes on smaller scales, on smaller distance from the center. And then what happens is that the supermassive black holes then kills them, both the little bars and the big bars. So this is why I call them as well heroes, somewhat. Okay, Samantha?
Yes, she's thanking for the explanation.
Perfecto. Great.
She's also asking about, I'm a bit unsure about the pronunciation, but Cepheids.
Seifert.
Yeah.
Seifert. Very good.
Yes.
Very good. This is Samantha, still Samantha. Samantha, this is a very, very nice question because we have been talking about active galaxies. So the difference between our Milky Way and active galaxies is that the process of accretion of gas onto black holes is more efficient. Okay, so this is the reason why they can be so more powerful. Now, generally, the most powerful active galaxies are called quasar, no, by quasi-stellar radio objects. But these are general galaxies which have become so consumed of gas, okay, that you can almost not see any spiral structure at all. It's just you can only see the big energy which comes from the very, very center. When the efficiency of this gas accretion onto the supermassive black hole is not as large, then the luminosity of this central black hole is very large, but not much larger than the whole galaxy. So you can still see spirals. And these are galaxies called Seifert, okay? And there are other types of galaxies which are active galaxies, we are called blazars. Now, there is as well a theory which is called the grand unified scenario of accretion disks that says that maybe the difference between quasars and Seiferts, it's not only or not just the difference in the accretion efficiency, but it could be the angle at which you see the system, okay? Because the black hole accretes and everything rotates like a disk because you have angular momentum. So if you see one galaxy edge on, okay, you see something. If you see the galaxy face on, then you have just a jet of material which is coming towards you. And you remember that I showed this. And why? Because every time that you have a process of accretion, since the inner regions of galaxy contain magnetic fields, the gas, before reaching the event horizon of the supermassive black holes, gets collimated away because the magnetic fields do like this. You know? So these jets are very strong when you see a galaxy face on, and very weak when you see them edged on. So this is what is called unified scenario for accretion disk, and can be another difference, a real difference between Seyfert galaxies, which emit much less energy than quasars. Ok, Samantha? Perfetto? Ottimo.
Do we have any other questions?
I mean, just I want to know something about the question. I think the question was about Cepheids, like the stars that pulsate, and you can like measure distances.
Okay, you see, this is why it's good. Sometimes with the echo. Okay, so I've been talking just bullshit for 5 minutes.
Yes, but like, could you just repeat again what you were explaining? Because I've heard of that also, but
I was explaining about the difference between different types of active galaxies.
Yes, but you used the word which sounded very similar. Seyfert, how?
Seyfert. Seyfert.
Ah.
Instead, it was Cepheids. And what was the question, Luke, about Cepheids?
I think the question was just how do they work? What's the like? How?
So Seyfert, bravissima, Samantha, you are still online. Very good. So this is the Cepheids. So with the C and H, and then E and then PH. Okay, these are pulsating stars. Okay. And these are as well stars which are on the edge of being unstable. You remember that I was telling that you have a lot of oscillatory motions in galaxies. Well, this happens as well on stars. Any object which is self-gravitating, so that is supported against the kinetic energy by gravity, is roughly in equilibrium, but it can be perturbed. And when you perturb, then it starts to do like this. It's like when you have, Samantha, a balloon, do like this, okay? You don't do anything, the balloon is in equilibrium, then you do like this, and the balloon starts to oscillate. Or you take trams, you know, the music of chup chup chup, you don't do anything, they are in equilibrium, you do like this, they start to oscillate. And actually, even the acoustic waves, sound waves, are this type of phenomenon. So Cepheid stars are very special type of stars which are not only pulsating like many other type of stars, but they are pulsating in a way that you can predict, because there is a very strong relation between the luminosity of these stars and the period of their oscillation. So why these stars are so important? Okay, so if I take a lamp and I go, and Julia is there at distance of 1 meter. Then Julia then goes at a distance of 2 meters. The brightness of the lamp decreases by factor 4, okay, because the light is distributed in a sphere of radius r. If the radius is twice more, the surface of the sphere goes like the square of the radius, so 4 times. So this means that when you see things very, very far away, they have very little brightness. But the fact that we have objects that we know have a very, 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 very constant luminosity, okay, this means that we can help us to calculate distances, okay, because if I have a Cepheid which is pulsating, okay, then I know I can calculate very well the period of cause, so I know the luminosity. These are called standard candles, okay? So when I have Cepheids in other galaxies, it is enough to measure their brightness and then just do the brightness times the distance square, and you can find the distance because you know the brightness, you know the luminosity, okay? The difference is just the square of the distance. You can easily calculate the distance. So other objects like this, so these standard candles, are supernova of types 1a, Okay, so supernovae are stars much bigger than the sun, which have been already exhausted all their hydrogen. Then they have fused, they have burned helium, they have burned a lot of things, and they have actually produced iron. They cannot do more than this, because to burn heavier elements than iron, then they would need more energy than the one that they produce. So the process would be endothermic. Okay, so then what happens? That they cannot burn any more heavy elements than iron. Then there is no enough kinetic energy, so the star collapses. When the star collapses, it gets very, very strongly shocked. And actually, the particles which are created, for example, neutrons and neutrinos of this neutrons decay, they actually emit so much energy, and they produce what is called a blast wave, which is almost as powerful as an entire galaxy. So this supernova 1A, they have as well a very, very universal luminosity. So for these supernovae, when you see them in other galaxies, you can easily measure the distance to the galaxy, simply because you measure the brightness, you know theoretically the luminosity, then you can provide the distance. Okay, so it is a thanks to this chain of standard candles, Cepheids, supernovae, that we can really measure how big the universe is. And it is thanks to this supernova 1A that one has understood that our universe is not only expanding, but as well accelerating. This is another story. Okay, Samantha? Bravissima. Good. Okay, shall we say taco hey? Are we tired?
Yeah, we are almost a bit over time, but if someone has a last question, you can ask that. But otherwise, I would just like to thank everyone for coming, to stick around, and I hope you learned something. I did, and I thought it was very interesting. So definitely a big thank you to Alessandro.
Ok, thank you very much. Ciao a tutti then. Arrivederci belli. Ciao.